Hello everyone, and we are talking about graphing rational functions. This is Unit 7, Day 3. So we've learned how to graph rational functions only so far by transforming the parent function y equals 1 over x. However, because a rational function can literally be defined by any function that has at least one variable in the denominator, there is an infinite number of ways that a rational function can look. So in order to be able to graph all of these, we kind of need to just follow a general process. And so the process that we're going to follow in this class is that we have to include all discontinuities, which are any vertical asymptotes or any holes. A hole is literally like a jump in the graph. It's where there is like very literally a hole in the graph, and we draw it as such. This will happen, as we'll see, when we have a set of factors in the numerator and denominator that cancel out. You have to graph either your horizontal asymptote if you have one, or if you don't have one, you have to graph the slant asymptote, and we'll talk about that a little bit more in the future. These are now no longer considered discontinuities because horizontal and slant asymptotes can actually be crossed or touched, but the graph does sort of approach them infinitely still, but they can actually be crossed over. So we'll see some examples of how that might look. Vertical asymptotes will never, ever, ever be touched or crossed, but horizontal and or slant asymptotes, they can be. So we can't always call them a discontinuity because sometimes, like I said, the graph will cross over them. Okay, we have to graph x and y intercepts, and we have to graph all lattice points, as well as any additional points that we might need in order to make an accurate shape of our graph. So how are we going to find all of these things? Well, very similarly to what we did before, to find the vertical asymptote, or the VA, that's the equation of a line, we're going to set the denominator equal to 0 and solve for x. That is still true. And sorry, I have failed to mention that the first thing you always want to do with all of these problems is factor everything and simplify what you can. The holes we get by taking a look at our factored rational, and any factors that cancel out will create a hole at that point. To figure out where that point would be, we set that factor that canceled out equal to 0 and solve for x, and whatever value we get, so wherever that hole is on the x-axis, to find out where it would be on the y, we plug that value into the simplified rational expression. So after we cancel it out, the resulting rational, we plug it in there and then simplify to find our y coordinate. And then we'll literally draw like a little circle right there to show that the graph doesn't exist there, but it exists all the way up to it and right after it. The horizontal asymptote for these, it's going to be a little bit different than what we did in the transformed parent functions. It's all based on the degree of the original rational. So we're going to go back to what we were first given, and we're going to compare the degrees. So we want to make sure that our numerator and our denominator are in standard form so that we can easily compare the exponents. So if the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote will always be the x-axis. If the degrees are equal in the top and the bottom, then the horizontal asymptote is going to be at whatever the fraction is of the leading coefficients. So let's just say your rational was y equals 2x squared over 4x squared. Your horizontal asymptote would be at 1/2, or 2 over 4. If the degree of your numerator is bigger than the degree of your denominator, you don't have a horizontal asymptote. In that case, you have a slant asymptote, and we find the slant asymptote by dividing our numerator by our denominator. So we can use synthetic if the denominator is a first degree binomial with no leading coefficient. If not, then we have to use long division. So once we do that division, the resulting quotient will be our equation of our line for our slant asymptote, and just ignore whatever remainder you get that is not part of the slant asymptote. To find the x-intercepts, we're going to set the numerator equal to 0 and then solve. And we just want to make sure if I'm asking you to write what the x-intercepts are, not just graph them, you need to make sure that you write it as a point with the x-intercept and comma 0. Y-intercepts we get by substituting x's for 0 in our rational and then simplifying to find the y value. And again, just like the x-intercept, if I'm asking you to state it, you need to write it as a point, 0, comma, and then whatever the y-intercept is. We'll go to our graphing calculators to find any lattice points or any additional points that we need in order to get an accurate picture of our graph by using the table function. So we'll enter in the original equation of our rational function and then go to our table to find any pertinent values. So most graphs are going to go from like -8 to +8, so any lattice points within that interval of numbers you're going to want to make sure that you include for sure, as well as just any sort of points that help us get a general shape of what the graph looks like. And that's it. That's kind of the steps that we're going to follow. This is going to take some practice. We have a lot of information that we need to find and a lot of different ways to find it. So use the little blue cheat sheet that I've given you as a reference, and let's try some of the practice problems in our packets. And come see me if you have any questions.